All right, so here was the question I posed at the end of the last part of this video. And so I hope you have figured out f sub x is this thing here, because this is basically like 5x again, because this whole thing is a constant when it comes down to x. With respect to x, y squared z cubed is a constant. So y squared z cubed remains as the first term of the derivative. Natural log of x becomes 1 over x. That is a miracle, if you ask me, actually. It's hard for you to imagine. I don't know if you think about this, but stop and think about this. Natural log, it's a logarithm based on e. The derivative of that happens to be the reciprocal function 1 over x. That is an incredible, incredible thing in mathematics. You should stop and think and just stand at awe with a mathematical structure like that, okay? Well, anyway. Of course, that means, the integral of 1 over x dx is the natural log of the absolute value of x. That's also incredible. All right, so that's f sub xy. We have just figured this out. And what else are we supposed to do here? I asked you to find f sub yz. So you take, oh yeah, so f sub y was, see this 2, 2 becomes the constant, right? So it's 2xy, z cubed is still z cubed, it's still there. Natural log of x disappears when you take the derivative with respect to y. And then you take the derivative of fy with respect to z, you get 6, 2 times 3, xy, and then z squared, right? Because z cubed becomes 3z squared. So that's what fyz is. So this is done, this is done. How about f sub xz? We don't have that, do we? F sub xz is the derivative of this thing with respect to z, so that becomes 3y squared z squared, and of course 1 over x disappears. That's done. Okay, how about f sub yx? So you take this thing and take the partial of that with respect to x, and that would be 2yz cubed, because again, this is like a linear function of x, right? Notice here, these are equal to each other, as we expected, thanks to the Clairaut, who proved the theorem. And this is just a verification of his theorem that his proof is correct. So that's done, right? Okay, so how about, let's see, f sub xyz. Do we have f sub xy? Yeah, from here, let's take f sub xyz. If you take the derivative of this with respect to z, you get 6y z cubed, right? Right, okay, so that's f sub xyz. How about f of z yx? We don't even have f sub z, so let's go ahead and find f sub z. That would be the derivative of that with respect to z. That's 3xy squared z squared. Okay, f sub zy is the derivative of this with respect to y. That's 6xy z squared. And then we take the derivative of that with respect to x. So you get 6y z squared. And you are very excited because you get the same thing as f sub xyz, which is the same as f sub zyx. All right, so even when you go into the third partial derivatives, third mixed partial derivatives, the order of differentiation actually does not change, and everything works out nicely, right? Okay, now just so you are familiar with this, and you will have plenty of exercises, it'll be differentiation drills that you will be doing for your homework. But there are a couple more things I should mention here. First, I want to review what happens here when you take the square root. Okay. Now remember, when you take the square, when you write the square root, it is the same thing as 1/2 power. So when you take the partial derivative, you just basically move this 1/2 to the front, and the new exponent will be 1 less, which is negative 1/2. Okay, but that's not it, right? You take the derivative of the inside function with respect to x. That would be 2. Okay, so then this and this will cancel. The answer will be 1 over the square root of 2x plus y squared. Just want you to know that. And then f sub y, okay, so think of this. Take the partial, it's 1/2. times this quantity inside the parentheses, negative 1/2 power, and then you take the derivative of this with respect to y. So it'll be 2y. 2 and 2 cancel, but this time you actually have the numerator, which is y. And then the denominator is the square root of that, which is inside of the parentheses. Okay, so I mean, these are not hard, but remember how you take the derivative of a radical function. Okay, and so you will be doing this many times throughout this chapter, and so you should be familiar with this. Okay, so one final thought is the interpretation. Okay, oops, something's wrong with my thing here. Okay, so you remember this whole idea of level curves or contour curves, right? So many times you will be seeing this type of chart. Okay, you have this function defined on the xy plane or R2, and then these are the three of the contour curves or level curves. You have a level curve corresponding to the value of 10, value of 15, value of 20. Okay, it seems like this 10 goes through the 0.32, 15 goes through the 0.52, all right? And so can you, for instance, find what 3 is? Okay. So the problem will say something like estimate f of 3, okay? Well, let's see, f of 3 is right here. I mean, 3 is right here, right? How do you estimate this? Well, the thing is we don't really know the answer. I mean, we don't know what the exact value is, okay? But we can sort of estimate it and we can extrapolate from this, okay? Because what happens is, if you look at, let's see, maybe right here, if you look at this point, this is between this and this, right? So think of this thing and the 10, so 3, f of 3, 2 is 10. This is sort of between that point and this is 15, right? Now, the thing is, maybe here, f of 3, 2 is equal to 10. And f of 3, what do you think? So here's 4. This is not quite 4, right? Maybe f of like 3.8 is like 15, right? So from these, you can extrapolate that f of 3 is probably somewhere between 10 and 15. And I would say, because it's closer to 15, I would say maybe approximately 13. Okay, that would be an okay guess. 12 is okay, 13 is okay, 12.5 is okay. But I think it's going to be closer to 15 than 10, right? Now, you still have no information about it, but if you have to guess, and by the way, this is how economists predict the future, biologists predict the future, epidemiologists predict the future of a pandemic, for instance. You know, they try to find the data points and then try to make conclusions by what we call a linear regression or extrapolation, because we don't have values for every single point. Okay, but that's what you can do with this. All right, now here's another question. What do you think f sub x of 3, 2 is? Okay, is that positive or 0 or negative? All right, now this is a very important question because this is the kind of question that will test your understanding, not just your knowledge, okay? So what does it mean? This is the partial derivative of f at 3, 2 with respect to x. The question is, okay, I mean, this represents the rate of change at 3, 2 in the direction of the positive x-axis. So you're right here. We know f of 3, 2 is 10, right? I mean, that's what the first contour curve tells us. But as you go in this direction, do you think the function is increasing or decreasing? Again, we don't know this for sure, but you can tell from here to here, it's going from 10 to 15, right? So you would guess, okay, again, we are not sure, but this is probably, if this function is a well-behaved function, there's no sudden ups and downs and so on that we can see. It's probably positive because at 3, 2, the value is 10, but at 5, 2, the value is 15. So it's going from 10 to 15 here. More likely, the local derivative with respect to x will be increasing. Right? So that's the kind of information you can get from this. All right, how about another problem? What is f sub x of 4, 2? Estimate this. Estimate f sub x of 4, comma 2. Now 4, comma 2 is right here, okay? And so how would you do that? We don't know the exact answer, but I know that f 3, 2 is 10, and f of 5, 2 is 15. If you figure out this point is right in the middle of this, then you can tell, yeah, you can tell that f of 4, 2 is probably 12.5. Okay, but you can approximate this by what? Find the difference between these. Okay, so this is 15 here, this is 10 here, and this is right in between those two, right? And the difference in the x direction is 2. This is my delta x, okay, because it goes from 3 to 5. And so this will be 5 divided by 2, or 2.5. And you can sort of estimate that the derivative, or the derivative of f with respect to x at 4, 2 is probably about 2.5. All right, how about f sub y at this point 4, 2? Okay, at this point 4, 2. Well, you know, again, here's this point. We don't really know, but if you go in this direction, it looks like it's going to increase, you know, because here's 10, you know, all these are points 10, and this is 15, right? So it's probably positive. Now we don't know for sure, so we'll just say probably. Okay, and that's because, again, this 4 is, the 0.42 is probably, the value at 0.42 is probably between 10 and 15, and it's going in the direction of 15. So we assume, or we can assume, that it is probably positive. I know these are sort of unknown, you know, things, and maybe you think it's not mathematical, but this is real. This is exactly how estimates are made, based on probability and science and so on. And so you should know what the interpretations of these pictures are. Okay, so that's pretty much it for section 3 of chapter 4. Okay, so we are at the end of section 4.3. You probably recognize that I did not address the question of, you know, how fast or what is the rate of increase at this of f at this particular point. If you go in the direction, if that direction is not in the direction of x or y axis, okay, what happens if you go sort of like 40-degree, 45-degree angle between x and y axis? Those are the questions that you would have to wait just for a little bit more to answer, okay, because we'll cover that in section 4.6 or something, 4.5. The next section, 4.4, is about linear approximation and tangent planes and so on, okay? But we will eventually talk about how to find the directional derivative, which is the rate of change in the particular direction, as well as you can see from this picture behind me, things like maximum points and the minimum points, absolute and local extrema, as well as the saddle points. So all kinds of good stuff is coming up in chapter 4 for any given, you know, multivariable function. All right, so look forward to what you can learn in the next section, section 4.4. But until then, I hope you have a great day and great week. I'll talk to you later. See you.